Let's look at a couple more graphing problems here. We want to find the first and second derivatives here to use the first and second derivative test. Before we dive in too far here, let's rewrite this as x squared plus 2 to the 1/2. Makes it a little easier to tackle that derivative. So here we go. Let's find the first derivative. So that's going to be the derivative of the top, which is 1, times the bottom, which is x squared plus 2 to the 1/2, minus the top, times the derivative of the bottom. Well, the derivative of the bottom is going to be a little chain rule here. So we got to take the chain rule for this bottom here, drop the 1/2, subtract 1, so we got 1/2 times x squared plus 2, subtract 1, negative 1/2, times derivative of the inside, 2x, all over the bottom squared. Well, the bottom squared is just going to be x squared plus 2 to the 1/2. The square root squared is going to make that square root go away. And there it is. Okay, before we go much further, we probably want to clean it up. So let's factor out the smallest. We got this parentheses here, x squared plus 2. Let's factor that out, and we want to take out the smallest exponents. So that smallest exponent is negative 1/2. So we're going to factor out x squared plus 2 to the negative 1/2. And we're going to multiply that times 1, or the leftovers will be 1 minus, I'm sorry, let's back up. Not so. We need a little bit more than 1. So we got a 1/2 power. So we need to subtract 1/2 minus what we factored out. 1/2 minus negative 1/2 is 1. So we have x squared plus 2 to the first. Now we factored this part out, so we're left with a 2x times 1/2 times x. Well, 2 times 1/2 is 1, so that would be just x squared. Well, that cleans up nicely. Look at that. Those x squareds are going to go away. Okay. So the x squareds are going to go away. Let me copy this down, x squared plus 2. So those are going away. And, well, what do we got here? This is interesting. So let's take this downstairs. And this is x squared plus 2 to the first power. Take this 1/2 down to the bottom. And we're going to add these exponents. So this is like 2/2 plus 1/2. We're going to have x squared plus 2 to the 3/2. Okay, see, we're going to take this downstairs. It's x squared plus 2 to the 1/2. And 1/2 plus 1 is 3/2. And what's left over on top after we move this downstairs? We have a 2. There you have it. So it cleaned up nicely, and now we're ready for the second derivative. But before we do that, let's go ahead and get our number line going on here. So we got our number line here for f prime. Always label it. And let's see, what will make this 0? Well, nothing will. What will make this undefined? Well, x squared is always positive. So this is always positive. It's never going to be 0. And we're taking a square root, so it's not going to be a negative. We do have to watch out. It's a square root, so it's always positive. So there is no critical value, so no mins or maximum, and it's just always positive. Okay, so we're always going to be increasing. Interesting. Well, let's keep going. Let's see what happens with the second derivative. So second derivative, we can rewrite this here as 2 times x squared plus 2 to the negative 3/2. So we rewrite there, and now we can use the chain rule. Drop the negative 3/2 down. Negative 3/2 times 2 is negative 3. Times x squared plus 2, negative 3/2 minus 1 is negative 5/2. Times derivative of the inside, which is 2x. All right? Yeah, that's it there. Okay, clean up. Let's clean it up. We can take the x squared plus 2 downstairs, and that's going to be to the 5/2 power. And on top, we have negative 6x. All right, that's f double prime of x. Now we can find the number line for f double prime. And what's happening here? Well, at 0, the second derivative is 0. So there's a possible inflection value. Let's find out what's happening to the left and the right. Again, this is the second derivative we're working on. Plug in a negative number, like negative 1. When you plug in negative 1, you get positive on top, and the bottom is always going to be positive. So the left is positive. If we plug in a positive 1 or 2 or positive 1, we'll get negative on the top, and the bottom will be positive. So negative or positive gives us negative. So that means we are concave up and concave down. Okay, so we're always increasing here, but the concavity changes. All right, so what does that mean? All right, so let's go ahead and get our graph. We can plug in 0 to get a starting point. If we plug in 0, we get 0 over the square root of 2, which is 0. So we know it goes through 0. We know it's always increasing here. And 0 is an inflection point. Okay, so this is inflection. And let's see. Is this always increasing as x gets bigger? Is this always going to be increasing? Well, as x gets bigger, this number here is, let's see, is the top bigger than the bottom? And what's going on here? Well, let's pull out a little bit of calculus here. What is the, since this is calculus, right? What is the limit as x goes to infinity of x over the square root of x squared plus 2? Well, as x goes to infinity, this small 2 doesn't matter, and so this is equal to the limit as x goes to infinity of x over the square root of x squared, but the square root of x squared is just x, or positive x, that is, and so this is 1. So we have an asymptote. Okay, so we don't need our calculator to tell us that. We just know that it's going up. It's going to be concave down. That's what this tells us, concave down. And it's always increasing, so it's always increasing towards that there. All right, what's happening as we go to the left? Well, it's also going to be concave down. It's always increasing, so it's got to be climbing up. It's going to go down to the left or up to the right. And this is going to have a limit of, or an asymptote of negative 1. All right, there you have it. So you can check on your calculator, but that's what it should look like. All right, let's take a look at our last one here. We've got a kind of interesting one here. We got e to the 4 minus x squared. Start out with our derivative here. F prime of x. Got a chain rule going on. Derivative of the inside would give us negative 2x times the outside, which stays the same, e to the 4 minus x squared. And we want to do our number line here. Find out when is this equal to 0? Well, it's equal to 0 when x is 0. So when x is 0, we have a critical value. Plug in a negative number. When you have negative 1, this becomes positive. And e is always positive here. E to any power is positive. Plug in positive 1, and you get negative 2. Negative 2. So it's negative. That's all we care about is negative. Okay, good. So what does that mean? That means we're increasing and decreasing. So we have a max at x equals 0. Great time for a second derivative here. Here we go. Second derivative. We're going to need some product rule, right? So derivative of the first would give us negative 2 times the second, e to the 4 minus x squared, plus the first, negative 2x, times the derivative of the second. Well, the derivative of the second is going to be what we already had. So it's going to be this whole thing here. So it's going to be negative 2x times e to the 4 minus x squared. All right, little cleanup here. Let's see. We can actually factor out this negative 2. Let's go ahead and do that. So we factor out negative 2 e to the 4 minus x squared. That leaves us with, notice we're looking at these two terms. We have a term here and a term here. And what's left behind? Well, we have a 1 for the first term. And we have a, well, let's see. We took out a negative 2, so we still have another negative 2 left behind. So this would be a negative 2. Let's go ahead and make that a minus. So a minus 2x squared. And we took out this e, we pulled it out. Okay, I think that's it. Double check if we distribute this. We have this times 1, we get this, yes. If we have this times negative 2x squared, we're going to get this, which is really a positive 4x squared, yes, indeed. Times the e thing, there it is. All right, there it is, we got it. So there's our second derivative. Okay. And we want to find our concavity here. So we set that equal to 0. What makes this 0? Will the first part ever be 0? Well, no, because e to any power is always positive. Can the second thing be 0? I think it can. So 1 minus 2x squared equals 0. Subtract 1. Divide by 2. Well, positive 1/2 and square root. So x equals 1 over the square root of 2, or multiply by square root of 2 to rationalize the denominator. Square root of 2 over 2. Okay. So which is about, this is 1.4 divided by 2, so it's about 0.7. So this is f double prime. So at the square root of 2 over 2 is a possible inflection value. Let's test it out. Plug in 0. Plug it into the second derivative. What do we get for 0? Well, that's negative 2 times e to the 4 minus 0. So that's going to whole thing be negative. Plug in 0 here, and we have 1. So this whole thing would be negative. Plug in positive. Let's see, this is about 1.4 divided by 2. That's about 0.7. Let's plug in 1. When you plug in 1, we get 4 minus 1 squared, which is 4. So this is always positive. So negative 2 out here, so negative. Plug in 1 here. We get 1 minus 2 times 1, which is negative. So we get negative times negative, which is positive. So what that means is we've got concave down and concave up. Well, let's see about our graph here. All right. So we'll plug in 0 just to get a reference point. And we get e to the 4 minus 0, so e to the 4th. E to the 4th, well, e is about 2.718. All right, so that's like 2.7 or 3 to the 4th. Boy, that's like 81, huh? Okay, so somewhere up here, e to the 4th, it's going to be about 81, 80-ish. Okay, somewhere up there. We don't need exact numbers there. Okay, but, all right, we got that. So what's going on? Well, at square root of 2 over 2, we have we've got inflection point. Okay, again, that's about 0.7. That's like 1.4 divided by 7. So we're going to have an inflection point here. We know it's decreasing and concave up. One more thing to notice here is, will this, looking back at the original function, will this ever be 0? And it won't, will it? Because as x squared gets bigger, like we put 1,000,000 squared, 4 minus 1,000,000 squared, all right? Well, that's going to be e to some negative power, which is just going to be a very small number because it's like 1 over e to 1,000,000. Okay? Same thing when we're going to the left side. Okay? So we're going to have an asymptote. at 0. So whatever's going on here, so this is the square root of 2 over 2. So it's concave up, and then it's concave down. All right, and there we go. Okay, and then what's happening over here? Well, you know what? I caught a mistake here. So we just convinced ourselves that this is going to go down to 0, going to the left side here. So it's got to be concave down. It's got to do the same scoop. So we're missing something over here. Did you catch it? Did you catch my mistake? When we square rooted, I forgot my plus and minus here. Uh-oh. That's going to change things here. So over here at negative square root of 2 over 2, if I pick a number like negative 1, I think we did 0 for this. If we pick a number like negative 1, and you plug in negative 1 to the second derivative, well, negative 1 is going to give us negative here, and negative here, it's going to be positive. Aha. So that's going to be concave up over there. And that's got to happen there because coming to the left, it's got to be increasing. It's going to be a mirror image. It's going to be increasing, and then at positive or at negative, somewhere over here at negative square root of 2 over 2, there's got to be another inflection point. Okay, so it's got to be concave down and then concave up. And there it is. Okay, and that's the graph. Okay, if you're plugging your calculator, I'm sure we'll get the same thing. All right, well, again, we got the first derivative. Find the mins and maxes. We do have a max there. Increasing and decreasing. Find the second derivative. That gives us concavity. Watch out, like we just had there. We'll have, watch out square roots. Okay, and putting it all together along with some limits to see what happens at infinity for the end behavior, we can get a pretty good idea of what the graph looks like. Great job. I know it's tedious, but keep at it and you'll get it. And you can master these functions and their graphs.